This presentation summarizes the key comparisons of the baseline scenario against the target or improved scenario. First, looking at indoor carbon dioxide on the left, we see a significant improvement. The baseline, represented by the blue bar, often exceeded 2,000 parts per million. The target scenario cuts this in half, bringing levels down to under 1,000 parts per million, a reduction of approximately 50%. In the middle chart, we look at thermal comfort airspeed. The baseline had very low airflow. The target scenario increases this by roughly 300%, reaching an airspeed of 0.3 meters per second, which greatly enhances occupant comfort. Finally, on the right, we see the impact on annual energy used for a block of 8 rooms. The energy consumption drops dramatically from over 172,000 kilowatt-hours per year, down to roughly 38,000. That represents a massive 78% saving in energy costs. Here is the area of focus in this study. Looking toward the front of the building, which faces north. The opposite side is the inside of the building. We use CFD Air Sketcher to investigate the pattern of flow in the area of interest. We input the coordinates of the building into the software. The software automatically extracts the wind data and creates windrows. We now know that the prevailing wind mostly comes from the east and southwest. We simulated the ventilation performance using prevailing wind from several directions. The top row shows the streamlines, the middle row shows the velocity contours, and the bottom row shows the pressure distribution. When we look at the velocity contours, especially in the yellow highlighted area, we can see that the interior of the building is dominated by dark color shades. This indicates very low air velocity inside the building, which means the ventilation performance is poor and the air inside the building is largely stagnant, particularly for the prevailing wind from the east. We stand at the front of the building, facing north, we can feel strong wind. However, when we walk into the building, there's almost no airflow at all. We initially had the idea of modifying the building, for example, by adding wing walls, but this would require a significant investment due to the large size of the building. Consequently, we introduced the Smart Classroom Ventilation System. It is an integrated approach that blends natural ventilation, exhaust fans, ceiling fans, and air conditioning. The reference classroom is 9 meters by 18 meters by 3 meters. With a total volume of 486 cubic meters, it typically accommodates 50 to 60 students. For ventilation, the system uses 4 exhaust fans with a combined airflow of about 5,000 cubic meters per hour, which is equivalent to roughly 8 air changes per hour. Air movement for thermal comfort is provided by 6 56-inch BLDC ceiling fans. Cooling is handled by 3 to 4 36,000 BTU air conditioning units, operated based on time and occupancy. The system is managed through a smart time of operation control strategy. Pre-cooling is done during off-peak hours, while a mixed mode of exhaust fans, ceiling fans, and air conditioning is used during on-peak periods. The system is also designed to be compatible with solar photovoltaic integration, ranging from 20 to 160 kilowatts at its peak. This slide explains the proposed solution, focusing on how the windows are operated under different conditions. During normal class operation, when air conditioning and exhaust fans are running, only 2 to 3 windows are open slightly, about 5 to 10 centimeters each. This is equivalent to roughly 10 to 20% of the total window opening. The purpose is to allow a controlled amount of fresh air to enter the room while still preserving cooling performance. Before and after class, the system switches to Purge Mode. In this mode, all windows are open between 80 and 100% for about 10 to 15 minutes. This allows rapid removal of carbon dioxide, excess humidity, and odors from the classroom. In cases of rain, high PM 2.5 levels, or when the outdoor temperature is higher than 35 degrees Celsius, all windows remain closed. Ventilation is then provided entirely by the exhaust fans using a filtered air path to maintain indoor air quality without opening the windows. This slide explains how the air conditioning system works together with the exhaust fans. When classroom doors are closed, the exhaust fans create forced cross-ventilation. This pulls stale air out of the room and allows fresh air to enter in a controlled way, even while the air conditioning is operating. Compared to using air conditioning alone, this combined operation significantly reduces carbon dioxide levels from above 2,000 parts per million to below 1,000 parts per million. The increase in room temperature is less than 1 degree Celsius, and the additional energy use is limited to only about 5 to 10%. As a result, the room receives fresh air and maintains thermal comfort at the same time, with only a small energy penalty. This slide shows how the system is manually adjusted based on the number of people in the classroom. When there are 20 people or fewer, 2 exhaust fans are used, providing about 5 air changes per hour. Ceiling fans operate at a low to medium speed. 0 to 2 air conditioning units are turned on, and the windows are opened by about 15%. For 21 to 40 people, 3 exhaust fans are used, giving approximately 6 to 7 air changes per hour. Ceiling fans run at a medium speed. 2 to 3 air conditioning units are operated, and the window opening is increased to about 20%. When a room is occupied with 41 to 60 people, all 4 exhaust fans are activated, providing around 8 to 9 air changes per hour. Ceiling fans operate at a medium to high level. 3 to 4 air conditioning units are used, and the windows are about 25% open. This approach ensures that ventilation, cooling, and comfort are matched to actual occupancy, avoiding unnecessary energy consumption while maintaining good indoor air quality. We understand that setting the system manually can be difficult and confusing, especially when multiple devices are involved. To make this easier for users, we developed the Smart Classroom Ventilation Advisor web application. The app helps users quickly decide how many exhaust fans, ceiling fans, and air conditioning units should be used based on time of day and occupancy. By entering a few simple parameters, the system provides clear, practical recommendations, reducing guesswork and helping users to operate the ventilation system correctly and efficiently. These are all 5 solution scenarios that were evaluated for the classroom. The first row shows the baseline variations, where there is no improvement to airflow. In the first case, we do nothing and rely only on the existing air conditioners. The air in the room remains stagnant, energy consumption is high, and carbon dioxide levels are high. In the second case, a small solar system is added. This partially reduces energy consumption and carbon dioxide levels, but airflow inside the room is still stagnant. In the third case, a very large solar system is installed to reach net zero energy. While this works on paper, it requires a very large investment and still does not improve indoor air quality. The second row shows the smart ventilation solutions, where airflow is actively improved. In the fourth case, which is the recommended option, exhaust fans and ceiling fans are added while keeping the existing air conditioners. This creates fresh air circulation, removes stale air, significantly reduces energy use, improves comfort, and achieves low carbon emissions with a relatively low cost. The fifth case combines smart ventilation with a small solar system. Due to the fact that the energy demand has already been reduced by smart ventilation, a much smaller solar system is sufficient to reach net zero energy with a lower overall investment compared to solar-only solutions. Overall, this comparison shows that improving airflow first is the most effective strategy. Smart ventilation delivers better indoor air quality, lower energy use, lower carbon emissions, and faster payback than relying on solar panels alone. This slide summarizes the environmental performance of each solution, focusing on energy use and carbon emissions. In the baseline case, energy use is at 100% and carbon emissions are high. Adding a small solar system reduces energy use slightly, but emissions remain moderate. Installing a full solar system can achieve net zero carbon, but it requires a very large investment and does not reduce the actual energy demand of the building. The smart ventilation option shows a different approach. By improving airflow and reducing cooling demand, energy consumption drops to about 22% of the baseline and carbon emissions are significantly reduced to a low level, even without relying on large solar installations. The ultimate option combines smart ventilation with a small solar system. Due to the fact that the energy demand is already minimized, This configuration can achieve net zero carbon with a much smaller solar capacity. From an environmental perspective, this comparison shows that reducing energy demand first has a much greater impact than simply offsetting energy use. Smart ventilation delivers strong carbon reduction while using fewer resources, making it the most effective strategy for the environmental pillar of ESG. This slide shows the social impact of each solution, focusing on health and comfort inside the classroom. In the baseline case, and in both solar-only options, indoor air quality remains poor. Carbon dioxide levels stay above 2,000 parts per million. This slide focuses on governance and finance, looking at cost and return on investment for each solution. In the baseline case, there is no initial investment, but the annual electricity cost remains high. When a small solar system is added, electricity costs are reduced, but the initial investment is significant and the payback period is long at more than 13 years. Installing a full solar system eliminates electricity costs, but requires a very large upfront investment and still results in a long payback period. The smart ventilation option shows a very different financial profile. With a relatively small initial investment, annual electricity costs drop substantially, and the payback period is about 1 year. This makes it the most financially efficient option, with fast returns and low risk. The ultimate option combines smart ventilation with a small solar system. This configuration achieves near zero electricity cost while keeping the investment much lower than a solar-only solution. The payback period is still reasonable at under 4 years. From a governance perspective, this comparison highlights the importance of responsible capital allocation. Smart ventilation provides the best balance between cost savings and return on investment, making it the strongest choice for sound financial decision-making under the governance pillar of ESG.